Hello everyone, welcome to day 3 of our training week, Healthcare NLP in Practice. We are very happy to have you here today. In today's session, we will be covering the following topics. The identify and obfuscate PHI in unstructured text, oncology research and treatment with Healthcare NLP, accelerating rare disease diagnosis. You can find the links to the slides and notebooks in the chat section. If you haven't yet received your trial license for the training, don't worry. I will share the link for that in the chat shortly. We will begin in about 3 minutes, and our first presenter will be Yiğit, who will start the session with the identify and obfuscate PHI in unstructured text. I wish everyone a productive and inspiring training day.
Hello, everyone. I am Yiğit. I'm a software engineer at Johnson Labs. Today, I will be covering the identify and obfuscate PHI in unstructured text across 2 sessions. We will explore how to fully automate the anonymization of both structured and unstructured clinical data using LLM-powered pipelines combined with healthcare NLP guardrails. We will also look at the patient and document level extraction, ensuring that the outputs are HIPAA-compliant, auditable, and ready for downstream analytics and research. Here is a quick look at today's agenda. In part 1, we will start by reviewing some fundamentals. We will define what PHI, PAI, and HIPAA mean, and then go over the HIPAA rules privacy rule. After that, we will discuss what the identified patient data actually is and why the identification is required in healthcare data processing. I will share a few peer-reviewed papers written by Johnson Labs to show how this topic has been handled in research. And finally, we will explore how we can identify unstructured clinical text using NLP-based methods. In part 2, we will go a bit deeper. We will look at how to identify both unstructured and structured data. What is PHI and PAI and HIPAA? PHI, Protected Health Information, is defined under the HIPAA, Health Insurance Portability and Accountability Act. PHI includes all information that can identify an individual and that is related to their health condition, treatment, or payments. In the USA, the identification of PHI is a requirement under the privacy rule of health insurance portability and accountability. The privacy laws of many other countries, including Canada, Australia, and European Union nations, also mandate the PHI the identification prior to its processing, analysis, or sharing. In the slide, you can see the common PHI entities, for example, medical record, age, doctor name, etc. What is the identified patient data? The identification involves removing PAI and PHI from data. Removing personal identifiers from health information helps mitigate privacy risks to patients. It also enables HIPAA-covered healthcare organizations, researchers, etc. to safely use the identified health information for comparative effectiveness studies, medical research studies, life science research, policy assessment, and other endeavors. The identification also enables these entities to share with each other without violating the privacy of patients. Finally, the identifying data before further processing eliminates the need for entities to get authorization from each patient. This reduces their administrative burden while ensuring that they have the data they need for their use cases. In this visual, you can see how the process works. First, model or pipeline identifies PHI entities in the original text. And then the one highlighted in the red are our PHI entities. Next, these entities are obfuscated with fake values. Finally, as you can see, the one highlighted in the blue have been obfuscated. For example, names like John Doe become Jack Michels, or dates replaced with different obfuscated dates. Why is it required? Key reasons: privacy protection. Removing identifiers reduces the risk of re-identification and protects patient confidentiality. Research and data sharing enables HIPAA's use health data in the comparative effectiveness studies, clinical trials, life science research, and multi-center collaborations without patient authorization. Label compliance. Many jurisdictions, HIPAA in the USA, GDPR in the European Union, PHIPA in Canada, mandate the identification before processing, analyzing, or sharing. Avoiding heavy penalties, failure to comply can result in the multi-million-dollar fines and reputational damage. For example, Anthem faced a staggering $16 million fine following a 2014 to 2015 cyber attack that exposed the personal health information of nearly 79 million individuals, the largest HIPAA penalty ever issued. Premera Blue Cross also suffered breaches in 2014 and 2015, compromising PHI of about 10.4 million people, resulting in a $6.85 million settlement finalized in September 2020. These cases clearly show the financial and reputational risk organizations face when patient data security is compromised. It's a strong reminder that protecting patient information is not optional, it is critical. The data de-identification process. Our data privacy process begins with a human-centered analysis, followed by software-assisted identification and human-controlled measurements. Next, we identify sensitive data using software, and finally ensure data security through continuous human-monitored oversight. This integrated approach guarantees privacy at every stage, from the collection of raw data to the delivery of the identified datasets. Customizing the ID models, iterative training workflow. When pre-trained models don't perfectly match your specific data patterns, this sequential workflow allows you to incrementally improve PHI detection, accuracy through custom model training, and rule refinement. Here is the sequential identification model enhancement process. First, we begin with pre-trained pipeline, and we get prediction from this pipeline. And then we upload pre-trained data for human view to GenAI. And after review, we train a specialized model on corrected annotations. And then we inject this NER into pipeline. After that, we add some rule-based annotators, for example, contextual parser, regex matcher for age cases. And then we evaluate the performance on representative samples. After that, we iteratively do these steps again and again until target achieved. Why this approach works? Pre-trained models have gaps in domain-specific PHI detection. This iterative workflow combines the strength of ML models for pattern recognition and rule-based approach for precise control. With each iteration, you gain both higher accuracy and deeper understanding of your data's unique PHI patterns. The GenAI Lab enables efficient human-in-the-loop annotation, dramatically reducing the manual effort typically required for custom model development. Peer-reviewed papers. We are proud to showcase our leadership in clinical text identification, validated by our recent publications in prestigious venues. For instance, our research accepted at ECIR 2025. By the way, I am the one of the writer of this paper, demonstrates the superiority of our medical language models, achieving an outstanding 96% F1 score for PHI detection, significantly outperforming major commercial APIs like Azure and GPT-4o. Furthermore, in our ML 4H 2023 paper, we introduced an automated identification system that not only registers substantially fewer errors than comparable solutions, but also exceed the performance of general-purpose models like ChatGPT. Our commitment to accuracy is further evidenced by our work in software impact, which we established a new state of art for name entity recognition across key industry benchmarks. These publications collectively confirm that our technology delivers the most accurate, regulatory-grade de-identification solution available in the market today. This is benchmark from can zero-shot commercial APIs deliver regulatory-grade clinical text identification. This detailed benchmark highlights the critical differences in PHI recognition performance across various platforms, specifically addressing whether zero-shot commercial APIs can meet regulatory-grade standards for clinical text identification. As you can see, our healthcare NLP solution consistently achieves superior F1 scores across all entity types, frequently reaching 0.98 and even 1 for category like age. This performance notably surpassed that of Azure, Amazon, GPT-4o, and Cloud 3.7 Sonnet, particularly in sensitive areas such as contact and location, which are often challenging for general purposes models. Beyond accuracy, we also demonstrate a remarkable cost efficiency. With healthcare NLP, be significantly more economical at just 2,480 per million documents, compared to the substantially higher cost of commercial alternatives. This data clearly indicates that while commercial APIs offer convenience, healthcare NLP delivers both unparalleled accuracy and cost effectiveness, making it optimal choice for robust, regulatory compliant clinical text identification. They identify unstructured clinical text. This slide illustrates the multilingual capabilities of our identification solution, demonstrating its consistent high performance across wide array of languages. As you can see from the F1 scores, our system maintains excellent accuracy, not just in English, but also across German, French, Spanish, Italian, Portuguese, Romanian, and Arabic. We exceptional results for clinical entities like date, street, and phone, consistently scoring above 0.98 in most languages, even for more challenging categories such as profession and organization. Our performance remains strong and reliable. This extensive linguistic coverage is a testament to our advanced architecture, ensuring that sensitive data is effectively protected regardless of the language it is presented in, which is crucial for global healthcare and research applications. They identify structured data. This slide demonstrates our capabilities in identifying structured data, which is crucial for protecting sensitive information in various datasets. Starting with the original table containing identifiable information such as SSN, name, date of birth, POB, and address. And then we see math table. Here, specific sensitive values are replaced with generic placeholders like medical records, SSN, etc. After that, we employ obfuscation, transforming the data into obfuscated table, where directly identified elements are replaced with synthetic data, effectively anonymizing individual entries while preserving the table's structural integrity, ensuring that no personal information can be traced back. And then we will start with unstructured data. I will go over from notebook. This is our clinical identification notebook. You can reach this notebook from GitHub Spark NLP workshop. Also, I will share the links from the chat. Yeah, it is already shared. In the first session, we load the required license. To use the identification, you need to have a healthcare NLP license. And then next, we install the PySpark and Spark NLP libraries. Before the session, I run the old notebooks. It is a lead notebook. After that, we import necessary modules and start the Spark session. You can give parameters into start function to Spark NLP GSL. You can see the Spark NLP version and GSL version. And yes, we start the Spark section. Also, you can start Spark manually using this method. Recommended the identification pre-trained pipelines. As a quick and simple introduction to the identification, we currently recommend 3 up-to-date pre-trained pipelines. These pre-trained pipelines include NER models, LLMs, and rule-based modules, with standard identification configurations already applied. Each pipeline runs with a just single line of code. This one, allowing you to input your data and get the identified output. No NER training required. The pipeline named Optimized, the first one, is designed to run efficiently on CPU. If you don't have access to GPU, this version still delivers strong results in both speed and accuracy. The pipeline with the large and medium suffixes are designed for GPU execution. They include built-in LLMs, and although they also support CPU, they will run slightly slower in that environment. It is enough just one line code. Let us look at this pre-trained pipeline. Here are the stages. We start with document assembler. I will explain these steps further. And then we, for example, in this pre-trained pipeline, we use 4 different NER models. And then we add some rule-based methods, for example, contextual parsers, regex matchers. After that, we merge all these results in chunk merger. Generally, we merge them according to their confidence level. And let us look at the possible entities of this pre-trained pipeline. Here, we make a prediction of these entities: location, contact, profession, and etc. Let us look at a simple example. Here is our text, and we annotate, and we can see the columns that we have. Yeah, this is the original one, and then masked column, and then the obfuscated column. For example, Hendrickson Aura is masked with entity name, and then it obfuscated Teresa Minister. We also this table in the presentation. Hold on, yeah. Here you can see how accurately PHI entities are detected across 8 different languages. If needed, NER models can be trained for other languages, and they are expected to perform with similar level of accuracy. And these are our pre-trained NER models. You can reach them with these links. Let me open one of them. Yeah. For example, we have a description and predicted entities you can see, and Python code, Scala code, and NLU code. Generally, customers use Python code. And then here are the results, example results, and we have model information, for example, language, size, input labels, and benchmarks. You can reach all NER models from model up. And let's walk through the NLP pipeline step by step. First, we start with the document assembler. The component takes the raw text from our input column and converts it to Spark NLP document format. This is the very first step required in any Spark NLP pipeline, because all downstream annotators expect the text to be wrapped as a document. After that, we take this column and we have the sentence detector. This annotator splits document into individual sentences. It is important because many NLP models, especially tokenizers and NER models, work best at the sentence level rather than a long block of text. After that, we apply tokenizer. The tokenizer breaks each sentence into tokens. meaning words or meaningful symbols that can be processed by the model. After that, we load the word embeddings model. Also, it's pre-trained. Here we are using clinical word embedding that were trained on PubMed's dataset. These embeddings help represent each token as a dense vector of number that capture the semantic meanings. So instead of treating words as plain text, we now have a numerical representation that captures similarity and context. The next stage is the medical NER model. We are using the pre-trained model called NER DID Generic Augmented, which was trained on N2C2 dataset for the identification task. This model recognizes different types of protected health information like patient names, dates, IDs, phone numbers, and so on in clinical text. Then we add NER converter internally. The NER model gives token level predictions, and this converter groups consecutive tokens with the same entity label into chunks. For example, if the tokens John and Doe are both labeled as name, the converter merges them into single chunk John Doe. Finally, we combine all stages into a pipeline. This pipeline runs all components in a sequence, from text input to sentence detection, tokenization, embeddings, named entity recognition, and finally, entity chunking. And then we create empty data frame, just fit the pipeline. Since Spark NLP pipelines require a fitted model before being used, then we fit the pipeline and store the resulting model. Once the model is ready, we can apply it to any clinical text to automatically detect, extract PHI entities. Let us look at our results. We transformed and select. Yeah. Let's analyze the PHI entities in a short sample text here. In this step, we are looking at the output of NER model, meaning the results will be tagged in IOB format. Let me briefly explain what IOB means. IOB stands for inside, outside, beginning, and it's a common annotation format used in natural language processing to label tokens as part of named entities. As I mentioned earlier, NER converter produces the final entity chunks based on these token level IOB tags. Here are our chunks, and then we can look at also, we have a vital in NER converter internal. We can filter these entities, these chunks. We have a set whitelist and set blacklist parameters. You can put your entities, and for example, you can exclude location entities in there. In another way, in this NER, we can blacklist and set location entity as a parameter. And then we create pipeline again, fit and transform, and let us see the result. Let us look at the results. In all labels, you can see the locations, but we use whitelist parameter, whitelist function. Yeah, you can see that we have no location entity in the whitelist labels. Masking and obfuscation. In the identification, we have two modes: mask and obfuscate. You can set it with set mode parameter, mask or obfuscate. As a short introduction, in mask mode, the detected chunks are masked. There are several options available to define how this masking is performed. In obfuscate mode, on the other hand, the detected chunks are replaced with different values. We also have many parameters to control obfuscation behavior, which I will show later on. Let's focus on the masking mode. Here we have a tool function, one of them, return entity matrix. This return a new column to save mapping between masked obfuscate entities and original entities. So if you set it true, in the final data frame, we have original chunks. Also, you can set the name of this column with this set mapping column. Let us look at the final our data frame, you can see we have the identified column and also out column. The out column is actually entity mappings column. But we didn't give any name. If you want to change this name, just use this column, this function. Let us look at the results. Here comes from sentence, here comes from the identified, and then you see this is original sentence, and then we mask found entities, date, name. And let us look at the mapping column. Here are chunks, original chunks, and their labels. We have a lot of masking modes. For example, empty labels, same length charts, fixed length charts, same length charts without brackets, empty labels without brackets. In order to show that, I added 1, 2, 4, 5 different identification stages and create our pipelines. And let us look at the results and compare these results. For example, in the identity entity label, we see date masking, and then if you use date same length, you will see asterisks in brackets. And if you use fixed length, only fixed asterisks you will see. If you want to use the ID entity label without brackets, there will be no brackets. And in this option, there will be no brackets, just asterisks. Re-identification. We can use re-identification annotator to revert back the original sentence. As input columns, we provide the return entity mapping column, returned by the identification annotator, and the identified output column, the output column of the identification stage. As a result, we obtain the original document. Here is the identification step results. Using multiple NER in same pipeline, I want to emphasize an important point in this section. One of the strongest aspects of Spark NLP is that its configuration are very flexible. It's like a puzzle. You can easily add or remove stages and adapt the pipeline to your specific use case in a way that is both simple and understandable. In this example, we use 2 different NER models in the pipeline. Then we merge their results with chunk merger. Let us look at it in a detailed way. Yes, this one is our first NER model, and then this is the second. But we use in NER conversion internal stage whitelist. We only get these labels and exclude contact and location entity for these NER. Also, similar example in second NER, and then we use chunk mergers. After that, we give chunk merger results to the identification. What is the input cost? Sentence, token, and chunks. And we use mask modes. Here is our pipeline. And this is coming from first NER. The NER, the ID generic augmented results. And this coming from second NER. And then this is coming from merger results. You can see all the labels, all chunks are found. And here is the final results, original one and the identified one. I want to give simple introduction, make simple introduction to chunk mergers. But if you're not familiar with the chunk merger, please check this notebook. In previous example, we saw the basic use of chunk merge. However, in real projects, especially when building production-ready pipelines, there is often a need to leverage its advanced features. Here I will highlight a few capabilities. Using the set ordering features function, we can prioritize results coming from different NER models based on their confidence scores. We give confidence scores and chunking in that. This allows us to achieve more accurate results without manually inspecting each model's performance on different entity types. Additionally, the set selection strategy methods let us choose how to handle overlapping chunks. For example, prioritizing the shortest or longest chunk. In the example above, we use two NER models, but this number can be increased as needed. We can also include predictions from rules-based models, LLMs, or other stages, and let the chunk merger select the most reliable entities. This feature directly affects the accuracy of merged output, making the merging strategy a crucial part of pipeline. In this section, we will observe how set regex override methods work, enriching with regex and override NER. First, it is important to note that our identification module already contains built-in regex patterns. These regex are designed to specifically detect PHI entities in the text. If we set regex override false, the NER-derived chunks are given priority over the built-in regex. If we set regex override true, the default built-in regexes take precedence and are applied to detect PHI entities. But ideally, we found NERs with in the pipeline, NERs rule-based methods. But of course, you can use this parameter and you can prioritize built-in regexes in the identification. Here are the original ones and masked ones. Also, we can add custom regex patterns to the identification model with set regex patterns dictionary. Here is our custom regex, and then we give the path to these methods. And we use set regex override true, prioritizing the rule-based regex rules. Here is our pipeline. And then in this example, we use custom regex. Also, you can use set regex pattern dictionary as JSON. In the previous example, we passed the path to TXT file containing patterns. However, in some environments, providing a file path like this can be problematic. Certain environment restrictions may make it difficult to write and read even a simple short TXT files. In such cases, you can this function and easily you can give your custom regexes. Also, you can set regex override true. We see whitelist parameter in NER converter internal, but now also you can use blacklist in the identification module. And these entities will be ignored for masking or obfuscation. Here are the results. And we will, right now, we will talk about obfuscation mode. In obfuscation mode, the identification model replaces sensitive entities with random values of same type. Before we dive into details of each feature, here is a high-level overview. Inside the identification stage, we maintain fake values for each entity type. Then we use those fake values to replace PHI in the text. Two important considerations in this replacement are HIPAA compliance, ensuring the obfuscation approach follows privacy rules, and consistency, making sure the same original value is consistent to map the same fake value when needed. Now we will go step by step through the parameters and capabilities that control how the obfuscation works. In this example, we give a small faker list. This is name and its entity, and we will write this obfuscation list. And after this example, we will give. This is a simple usage of obfuscate. We just set obfuscate mode and give NER chunks to our identification module. And again, same example, sentence, and obfuscated one. For example, David Hale obfuscated to Sherida freshwater. Also, we obfuscated age 25 years old, 27 years old. We have lots of parameters for obfuscation. Obfuscation ref source. This pet is our obfuscation list pets, and there. This is the obfuscation ref source. First, set obfuscation ref file lets you provide an external file containing the exact set of replacement values you want to use. A second, the set obfuscate ref source controls the source of fake values. The options are faker, in the faker mode, use the built-in faker generator to produce realistic looking values on the fly. This is default. And you can set its file, use only values from the file you provided with set obfuscate ref file. And also you can set both, combine both sources, use values from the file when available, and then fall back to the built-in faker otherwise. Here is the result. For example, in the faker mode, the faker mode allows the user set of fake entities that we mentioned before. If we set obfuscate ref for faker, the entities that are allowed right now are the followings. We support these entities for obfuscation. There are lots of, almost every entity we support. Also, we have a set obfuscate date. If you want to obfuscate that, you should set it to. And you can use these methods: set keep year, set keep month. For example, if you set to true, the years remains unchanged, ensuring consistency in data that relies on year-specific information. Here are simple sentence. And in this example, we use faker, so default mode. Selective obfuscate ref source method to allow per entity customization of obfuscation source. This enables users to specify different obfuscation strategies for different entity types. In this example, for example, for obfuscation of patient entities, we will use file. Or if in obfuscation of data entities, we will both use faker and custom lists, custom faker lists. And we give this dictionary to set selective obfuscate ref source parameter. Return mask field in metadata. Metadata masking is implemented in the identification process through the set metadata masking policy function. This feature enables users to add mask option to DID within the metadata, providing enhanced data privacy measures. Let us look at the results. We set entity labels. As we mentioned before, we have a 5 different masking strategy: entity labels, same length charts, and fixed length charts. Here, we took this info from metadata, and we get masked value from there, and you can see the mask values. Use full pipeline in the light model. With this code snippet, we are using a light pipeline to run our identification model in a lightweight local mode. Unlike a full Spark pipeline, the light pipeline doesn't require Spark session or distributed processing, which makes it much faster and ideal for testing or small-scale inference. Here are the results. It's a Python dictionary results, and then age group obfuscation. In this example, we are using the set age groups parameter to define custom age to category mappings. For instance, ages between 0 and 1 are labeled as baby, 1 to 4 as toddler, and 4 to 13 as a child. And then go on. When the identification model processes the text, it automatically replaces numerical age values with the corresponding age group labels. So, for example, age 17 becomes, let us look at one example, age 17 becomes teenager, and age 55 become adult. We have a set age range parameter. With the set age range parameter, we define the boundaries for age obfuscation. This means that each age value will be replaced with another random number with the same specified range. For example, a 15-year-old might be changed to 12 or 18, but never to 60. These are our boundaries. And let us see the identified results. Here. For example, 15 obfuscated with 19, or 4 obfuscated with 7. Because we define the boundaries of these ages: 1 to 4, 4 to 12, 12 to 20. The HIPAA privacy rules mandates the age from patients older than 90 years must be obfuscated, while age for patients 90 years or younger can remain unchanged. If the parameter is set true, age entities larger than 90 will be obfuscated as per HIPAA privacy rule. Here is our parameter, and we set true. And let us look at the results. As you can see, we only obfuscated plus 90 ages. 92 obfuscated with 98. But 4 remains same. Name chunk obfuscator. Name chunk obfuscator annotator allows to transform a dataset with an input annotations of type chunk into its obfuscated version by obfuscating the given chunks. This module can replace name entities with the consistent fakers, remains other same. Here is our obfuscation faker list, and then we give this list to name chunk obfuscator. This is just for name obfuscation, but also you can do this in the identification stage. You don't need to use this separately. For that reason, I will skip it a little fast. Yes, you can see, for example, John Davis obfuscated with Blankenship, but we define Blankenship in name obfuscation list. Shifting pace. We replace date entry another date randomly. But instead of that, we can shift the date according to any column. Here is our sample data frame, and we have a patient ID and text. But in order to shifting dates according to patient ID, we use this pipeline. Here we are using document hashcoder to generate consistent date shifts based on patient IDs. The set range dates parameter, we define the range of dates from which the date shifts will be sampled. The set patient ID column method specifies the column in our data frame that contains patient IDs, ensuring that the same patient always gets the same shift value. This provides consistency across documents. By setting a seed value using set seed 100, we make the randomization deterministic and reproducible. This is document hasher, and we give the output column to our other steps, and we set use shift function to true, and create our pipeline, feed, transform, and let us look at the results. We obtain new column called shift days, which contains the generated day shift values for each patient. If we then set the parameters at use days to, it will apply these shift days. You see the patient ID, and they are the same, but if patient ID is changed, shifting days will be changed. Also, instead of shifting days according to ID column, we can specify shifting values with another column. We give these numbers manually, and here is our sample data frame, and we create our pipeline, and again we set it true, and let us look at the results. Day shift column, we gave these day shifts manually, and for example we can look the first one, we shifted 10 days and obfuscate with day shift value. Custom date format support for data obfuscation. This parameter to allow specifying custom date formats in addition to the built-in date formats. This enables more flexible parsing and obfuscation of non-standard or region-specific date patterns. For example, we have different date patterns. This is our sample, and I guess we need to give a break. This is the last feature that I will mention, and I will skip it. Part 2. Yeah. With this function, we can give date formats. You can give every date formats, whatever it takes, and we will the identification will be obfuscated according to these formats. And here are the results. We can correctly obfuscate these dates. I guess this is the end of the first session. Then we will cover advanced features of the identification, and then I will skip structured identification. And then I will show some demos. Hello everyone again. In this session, we will have a multimodal identification, and then we will skip advanced features, and then I will open the structured identification notebook, and we'll continue from there. And then I will show some demo from our website. Yes. In multimode identification, we have multimode functionality in the identification by providing a JSON file to the set selective obfuscation mode parameter. We are able to use multimode identification. This is an example JSON file. In this configuration, we obfuscate font, we will mask ID, we will skip date, we will do anything about date, and we will use mask same length chars in name entity and mask fixed length chars strategy for zip and location entities. Let us start with first example. This is our configuration JSON file, and this is our pipeline, word embeddings, NER model, and we put blacklist, contact, and then yeah, we give the our configuration JSON files to selective obfuscation modpad. We create our pipeline again. Spark data frame, fit and transform, and here is our results. For example, we will do anything about dates, but we mask name with asterisks, as you see, and we obfuscate font with different numbers. Not to identify a part of entity. Sometimes we may not want to identify some entities. For example, according to HIPAA rules, we don't have to identifiers. So let's show an example how we can skip the identification of entity. And we can create a contextual parser. In this, we created a contextual parser for in order to find here this contextual parser. This is our example sentence 2005, 2025, and with contextual parsers we found the entity here, but you can check contextual parser if you want to understand how it's works. And then we put this contextual parser in our pipeline. First, we will merge chunk merger and NER generic chunk, and chunk merger will give the precedence to the year chunk. And other NER, I think it's more understandable if you look at these results. Let us look at the results. This is our sample paragraphs. And here, these are found by contextual parser. It's found only here. And these are found or detected by NER, DID generic augmented. As you can see, full dates. But also we have only years. And after that, this is our merged results. For example, if you want to see, if you see entity dates, but this one entity is year. And in final merge chunk, we exclude the year. Where I want to go, yeah, In final chunk merger, we exclude, we put year blacklist, and then in the final merge chunk, we don't have any only year entity. And let us look at the results. For example, sixth row in 2008, you see that we don't obfuscate this year. Or let us look at this row. Yeah, this one stay same. But if you look at the other dates, for example, this one, we mask these dates. Unusual pattern usage. Medical text has a complex structure. Sometimes our DIG in any model mistakenly identifies certain entities as dates, such as test results or dimension. In such cases, we utilize a rule-based NER contextual parser or regex feature. This is our example data frame, and then we write the contextual parser rules. Also, it's a dictionary, and then we give the dictionary to contextual parser. Then we found test results chunks, and also we use NER model, and then we merge them. Let us look at the results. Yeah. These are coming from NER, and these are coming from contextual parser. And after merge this, we see all the entities. But you see the labels is different dates coming from NER. Test results is coming from contextual parser. This is the visualization version of the results. This is another example of multi-mode identification. We will obfuscate date, and we will skip test results. And here we get the intended results. Yeah. As you can see, we do nothing for these test results. They are same. But if you look other dates, for example, this one, this is birth, date of birth, and we obfuscate with different values. Yeah. Advanced features. These are generally about consistency. This section, yeah, it's highlight the key enhancements, new functionalities, and performance improvements that have been introduced in recent releases, helping users understand the evolution of the identification capabilities. Objectives. Summarize important changes in the identification models and pipelines, demonstrate new features with practical examples, and help users easily adapt the latest advancements for their anonymization workflow. And please make sure the run the notebook Healthcare NLP 6.3.0 or higher. In this pipeline, we use pre-trained zero shot. This is an actually LLM, and we can give labels. You can give any label and put these labels to set labels methods. And after that, of course, we need to use NER converter internal. Let us look at the group by mechanism. It supports consistent obfuscation within groups using the group by column parameter in conjunction with consistent obfuscation and consistent across name parts. The group by parameter allows partition the dataset into groups based on the values of specified columns. This is our example data frame. You can see that this column file 1, file 2, then we have 2, file 2. We group these rows and set group by ID. By group by ID, we set these column to the identification. And let us look at the results. Yeah, for example, these are file 1, file 1, file 1. And as you can see, for example, patient John Doe will always obfuscate to Ronald Stanley in these groups. And you can see same John Doe, Ronald Stanley. But in other groups, consistency is not supplied, is not supported. Inferring missing PHI entities via previously detected NR outputs within the identification. Set chunk matching. This feature allows chunks like name and date to be inferred in contexts where they are not directly detected by NR, by referencing previously identified chunks within the same group. For example, if name was identified earlier in the document, similar text later in the group can be tagged accordingly, even if the NER model missed it due to lack of context. Here, how we can use this parameter. This is our entity, and this is our confidence threshold. This is especially useful name and date entity, and also it requires set group by column. This is our example text, and this is our pipeline. And let us look at the results. This is before chunk matching. For example, yeah, they identified. Yes. As you can see, in this date, NR couldn't find this date. But for example, in created one, we have same date entity. And with this chunk matching, we set the date, and it is confidence must be higher than 10.50. And after chunk matching, you can see that we can catch the date and mask the date. Improved name consistency handling in the identification. We have improved the way fake names are generated and assigned during the identification process. Previously, name tokens, first name and last name, were treated as a single chunk when generating a fake name. Now, each component of name is processed individually and then recombined into full fake name. This enhancement allows for more consistent obfuscation within documents, even when only partial name mentions appear, John Smith or Mr. Smith. As a result, the same fake entity components will be used throughout the document for same real-world identity, improving coherence and readability while preserving privacy. This is an example. John Smith obfuscated to Lion Brow, but if we see the John separately, we will obfuscate it Lion, and also Smith will be obfuscated Brown. It will be more understandable in the results. Here are text, and let us look at the results. For example, let us look at the second row. You see the John obfuscated to article, but our group includes John Smith. Before sentence, in first sentence, we see that it's obfuscated arteries, and when we Smith is separate, we see that it is also obfuscated to layer. This ensures the consistency. Geographical obfuscation for location entities. This ensures realistic and coherent obfuscation of geographic entities. This feature guarantees that obfuscated addresses make sense by maintaining valid combinations between state, city, zip, street, and phone. Language requirements, you need to set it true, and this is only supported in English. And again, let us look at the results. This is results from before geographical obfuscation. Yeah. If you look at these results, we can see that the address is inconsistent. For example, West Leslie, Hart, Texas. A quick search would reveal that this is a fake address. But after geographical obfuscation, we set it true, and also we set it counter obfuscation false. And after geographical obfuscation results, the obfuscation address appears realistic and geographically consistent, making it much harder to identify as a fake. Static and file-based obfuscation pair support in the identification. With the pairs list, we supplied explicit original entity type replacement mappings, so we can reach the obfuscate chosen names or entities to the exact values we want. For example, using your list above, John Smith will always replaced with Andrew Snow, whether labeled patient or name. And Los Angeles will always become New York City. We can define this manually. And let us look at the results. Yeah. As you see, John Smith is always obfuscated with Andrew Snow. And also Los Angeles always obfuscate with New York City. This feature is especially useful in VIP or high-profile patient scenarios, where specific sensitive names or locations must always be replaced in a controlled and reproducible way. Support for obfuscation equivalence to normalize entity variance in the identification. For example, Robert and Rob will be treated same. Let us look at use case example. Alex and Alexander will always map to the same obfuscated value under the name, or CA and Caliph normalized to California under state. How it works, accept a list of strings triples, variant, entity types, and canonical. Both variant and entity type are case sensitive. And let us look at the equivalent list. For example, NY city will be treated as New York, or Liz name treated as Elizabeth. And we give this equivalent list to set obfuscation equivalence. And also you see that we have a gender awareness parameter. It will be according to obfuscate, according to gender. And for example, when you see Dr. Liz, we have Dr. Liz obfuscated with Dr. Rosa. And when you see Dr. Elizabeth Carter, it's a long format, long version. It's again Dr. Rosa, because Dr. Liz treated as Elizabeth. Liz treated as Elizabeth. Deterministic fallback for missing page shift in the identification. This feature is especially useful in the identification pipeline where page shift must be consistent per ID. Some rows have null or missing shift values. Here is the logic. If another row with the same ID has a shift value, it is reused. But if no shift exists for that ID, a fallback shift is generated using deterministic hash function based on the ID and fixed seed. Here is the example data frame. We have a values for first two rows, but there are some non-values in our data frame. Yeah, we filled these null values with this algorithm. Improved case sensitivity for fake data generation in the identification. Enhancement, fake values generated during obfuscation now respect the original text casing by default. This ensures that fake data matches the case style, lowercase, uppercase, mixed case. And again, this is our pipeline, this is of the identification stage, but it works as a default. You don't need to add new function or parameter. Yeah. When we look at the results, David Hale, as you can see, all lowercase, or Maria uppercase, and you see that Elmo all are uppercase. We will look at structured identification in different notebook. So for I skipped this session. Pre-trained pipelines. This table shows the speed benchmarks for the pre-trained pipelines, including which machine they run on, the number of partitions, and how fast they process the data. You can also see which modules are included in each pipeline. The key point here is that NR modules take significantly more time to run compared to the other module, while the rule-based modules in the pipeline have only minimal impact on overall processing time. We can look at the example. Here is our machine. These are the versions. For example, for the identification one, chunk merge. Yeah, we can look at. You can see the time benchmarks. We have a 1 NER, we have a 3 NER, and you see that the speed comparison. You can reach this protein pipeline from these links. Also, we have a description, predicted entities, and demo. You can access all info about this pre-trained pipeline from this page. Clinical identification multimode output. This pipeline simultaneously produces masking with entity labels, fixed length charts, same length chart, and obfuscate version of text. Strategies of masking and obfuscate versions. We will see these. Here is the single pre-trained pipeline one-line code, and you can look at the stages. As you can see, we have 4 different identification in order to show different masking strategies and obfuscation. And let us look at the results. Here we have 4 different results, and you can see all the masking and obfuscated results. Here is the entity label, asterisk with no brackets, and obfuscated. Pipeline tracer and pipeline output parser. Automating pipeline tracer analyzes pipeline tracer to help return structured JSONs from pre-trained pipeline via the pipeline output parser method. Pipeline tracer is a flexible class that tracks every stage of a pipeline. It provides a detailed information about entities, assertions, identifications, classification, and relationships. Pipeline output parser. Some of the central functionality includes printing the pipeline schema, creating pipeline dictionaries, and retrieving possible assertions, relations, and entities. We have another notebook for pipeline tracer and pipeline output parser, but we will look at again. Yeah. We give the ID pipeline to pipeline tracer and call create parser dictionary. And here is the final dictionary. And then we have a column maps. And then we give this column map to pipeline output parser. After that, we call run function. And as you can see, these are the dictionary type NERs. And which makes integration with other APIs easier and helps standardize the workflow. We can see all the results from there. And exception handling. With exception handling, if an issue occurs in a document, the code and process don't stop. Instead, the error is handled and processing continues with the next document. The identification is a well-established and frequently used module, so the likelihood of bugs is very low. However, in such cases, as a safety measure, exception handling can be set through. This is the end of the unstructured clinical text identification, and now we will skip the structured identification. Also, you can reach these notebooks from GitHub and share links. Here we upload our license and then again install necessary libraries. And this cell, we got the MySQL jar connector and then Spark session. These are the same. Also, you can set it manually. Start Spark session manually. Yeah, we download the example table from GitHub, and this is our data frame. And then we import structured identification. Let us look at these parameters. First, we pass the Spark session as a parameter. Then we provide a mapping of our data frame columns, where the key represents the column name and value represents the corresponding entity type. Finally, with the obfuscation ref source parameter, we specify the source to be used for obfuscation. This can be faker, file, or both, depending on the setup. After obtaining our obfuscator, we pass our data frame to obfuscate columns methods. Finally, we use show to display the obfuscated data frame. Let us look at one of the example. Cecilia Chapman obfuscated with Washington stance. This is very easy when we compare it to unstructured the identification. And this is another example. This is our faker list, name and entity type. We provide our own faker list for obfuscation. We set the obfuscate resource parameter to file, meaning the obfuscator will only use the faker values from the list we supplied. We also define a column seed to ensure deterministic obfuscation, so the results won't be random. Let us look at the results. Yeah. This is the obfuscated data frame. Also, we can shift end days in structured identification through days parameter when the column is a date. This is our simple data frame, example data frame. And then, as shown in the table, yeah, we assign days to 5. And as shown in the table, all dates were obfuscated to 5 days later. With output as array, we can choose to receive the results as an array. If we prefer, we can output the obfuscated columns as separate columns while keeping the original ones in the data frame. The overrides and suffix parameters control this behavior, allowing us to either overwrite the original columns or create new ones with a custom suffix. Here you can see the parameters. We set it false and add suffix. These are the original columns, and these are the obfuscated columns, and we will not overwrite them. Key additions to include options for regional data formats, region, selected data obfuscation, keep year, keep month, text length, preservation, keep text size obfuscation, faker length offset, gender aware name obfuscation with gender awareness, and HIPAA-compliant age anonymization with age ranged by HIPAA. For example, keep year true. When we look at the original, yeah, these are the same. But if we set it false, oh, I need to run. No. So low. So forget. Let us run this again. And we can continue from this notebook. Let's see. And after that, structural identification for relational database. We will install MySQL server dependencies, and then start MySQL, some database configurations. It's done, and create a database. These are the takes data. Here's our example data frame. And let us import the database data, the identification utility model, then set up the relational database, the identification options. Here's the configurations. And this is the original table. And this is the identified table. We can configure this according to this dictionary. And we give this config to the relational DB identification, and then run the identify function. And according to these rules, we identify table. And second example, this is the original table, and we masked these columns. Yeah. As I mentioned, according to the unstructured clinical identification, structured identification is more easy. And now we will look at our demo page. You can reach there from our website, solutions, the identification. Try leave them. Yeah. At the beginning, we showed how to identify. You can test your dataset, but never enter real PHI data. When we click this button, we see the one. Yeah, here is the masked version. Hospital and the address, we detect the address, granular street, city, state, country. And let us look at the obfuscated text. Harvard Hospital obfuscated the collision psychiatric hospital. But as I mentioned, these are standard configurations. You can configure the pipeline according to your necessity. Also, you can, this is the structure, data, the identification, original one, masked one, and obfuscated one. For demo, you can write info@johnsonwallet.com. And also you can identify PDF documents using GDPR guidelines by analyzing PHI information using out-of-the-box Spark NLP and Spark OCR model. As you can see, PHI entities will be hidden. Also, you can identify DICOM documents by masking PHI information on the image by either masking or obfuscating PHI from the metadata. Here is the founded entities. I'm looking at the questions. Are label consistent through data? One of the questions I'm reading. Can the obfuscation versions of tabular structured PID provide mappings from input to output? Example, John Doe gets obfuscated to John Martin. Is there a simple way to get the mapping from the model? Are label consistent through the data? John Doe always gets obfuscated to John Jordan Martin. For this functionality, we are using seed parameters. Let us see again. For example, we set column seed 23. When it is set seed column, you will see that John Doe always gets obfuscated to Jordan Martin in every entity. Another question, when we talk about custom date format support, what is the built-in date format support by GSL DID models? Actually, we have a lot of date formats. We support almost all date formats. But sometimes these are, as you see, these are very different date formats. But generally, we don't see any unsupported date formats. But if this case occurs, you can set it with set additional date formats, whatever you want. It's for obfuscation, of course. Where should we start on the GitHub? Let me open our GitHub. In Spark NLP workshop, tutorials, certification training, healthcare, and you see that all notebooks that we have, and with let us look at the identification. We have different notebooks for the identification, but for start, you can use this notebook. You can see you can use this notebook, but yeah, we have links in the chat. Also, I will share some other links. Let me open Teams. We have lots of blog post papers about the identification. I will share these links. I can't find the agenda. Can you please let me know what will cover in the last one, please? Seriously, how do we choose which one iteratively? How do you choose which one to iteratively fine tune? Yeah. I will explain this using multiple NERs. As I mentioned, for example, percent model. Let us look at the percent recommended identification pattern. Generally, in the projects, we use your custom NERs, and we support these NER results with these pre-trained models. But it changes according to your data, because as you know, end types can be changeable. And for that reason, for example, we use one of the medical NERs and use set and blacklist parameters, and we exclude the low accuracy entities with these parameters. Equivalent list grow large. Equivalent list, let us look at this. Actually, it doesn't affect the performance. You can upgrade this list, but this will be no problem. Possible to different offset values for each RET. This will ensure the transform. After the session, I will give detailed answers for questions. There are lots of questions there. Thank you for listening. It's the end of my presentation session. And Mohammed will continue with oncology research and treatment with healthcare NLP. Again, thank you for your listening. And again, I will answer all questions after the session.
Hello, everyone. I'm Mohammed, and I'll present the next presentation. Let's get together in 12 minutes. Okay. Okay, so hello everyone. I'm Mohammed. I'm working as a senior data scientist at the healthcare team at Johnson Labs. And today I will have the session about the oncology research and treatment with healthcare NLP. I will try to present some use cases, real world use cases, and we will try to solve those problems by using the healthcare NLP library. So here is the agenda. We will start with a short introduction, and I will share the case study samples. And after that, we have two different case studies, real-world case studies, and one for analysis based on the cancer types, and the second one is creating the biomarker table. And then we will jump into the code, and I'll try to show how we can leverage the NLP, healthcare NLP library for solving these problems. And as you know, according to the ORL media and the downloads on PyPy, Spark NLP is like most widely used NLP library in enterprise. And according to the gradient flow, like 54% of the Gen AI in healthcare projects, the company is using Johnson Labs. And we have 25 benchmarks and peer-reviewed papers, so we provide the best accuracy for our solutions. And you can find some peer-reviewed papers we have, like you can click on here and see all of them on our webpage. And some of them are related to the clinical de-identification, some of them are for assertion detection and ANER and adverse drug events. You can check all and try to understand the architecture at the behind we use and how we approach these kind of problems. On the other hand, Johnson Labs organizes the NLP Summit for each year, and there are many global companies who works with us, and they present their use cases in that NLP Summit, like for example, Roche or Mount Sinai or MIBA. And like if we mention some of them, like for example, Roche, they demonstrate how healthcare specific LLMs address key challenges in oncology care by analyzing the unstructured EHR data. And these models like build accurate patient timelines from fragmented clinical notes and match patient profiles with up-to-date NCCNs, like National Comprehensive Cancer Network guidelines for personalized treatments. And this approach transforms raw data into actionable insights, improving precision and quality in cancer care. And on the other hand, like MIBA, they presented AI-enhanced oncology data showcases. They are leveraging an AI pipeline that extracts and enriches the key oncology data from unstructured EHR text and scans. And they use the NLP and then hybrid. Actually, they are using a hybrid approach, NLP plus LLM models. So it identifies crucial details like staging, biomarkers, and adverse events. And this system improves the clinical trial matching and transforms raw healthcare data into actionable insights for better patient outcomes. If you are interested in these kind of oncological case studies, you can just check on YouTube or on our webpage. You can find the recordings and the details of their work. So here is the first use case that we will cover. This is about the analyzing oncological entities and disease progression. Let's assume that you have many clinical documents, you're working in a hospital, and you have many oncological data set, unstructured text, and you want to de-identify, you want to identify the disease progression, okay, for like treatment plannings, individual treatment plannings, and you want to check how the metastasis spreads on the cancer patients, like oncological patients, by using their clinical notes, you want to get some like pattern, okay? And you would like to you're just interested in the metastasized cases. So and you want to check on which body part when the cancer metastasis spreads to. So first of all, in this use case, there are some clues in our problem, right? Like disease progression, where cancer has metastasized, and you want to filter the documents which mentions metastasis, and you want to identify where it spreads to, like on which body part, right? So after all, at the end of this process, you can find a pattern to prepare a personal treatment planning beforehand the cancer was metastasized or for further patients. Okay, so we will use these clues for solving our problem. Here are the stages that we will follow. Like first of all, we have like we may have thousands of oncological clinical notes, right? And we want to just find the where the metastasis spreads to, right? So first of all, we need to filter the documents which mentions metastasis, right? And after the metastasis filtering, then we will check the oncological entities and also the body parts. So we will use NER models for this. And after the entity extraction, we of course need to check the assertion status of those extracted oncological entities, because sometimes doctors in the clinical notes, doctors mentions about the family history, or the oncological entity may be related to someone else, or it was already mentioned like it is not appear in the patient. So we need to drop those kind of entities, and then there may be some more in this same document. There may be more than one oncological entities and also more than one body part entities, right? So we need to check those entities if they have a relationship or not, right? To create a to check to get some insights for the metastasis use case, right? If it is spreading to the other body parts. So after getting the entities and the relationships as an optional, sometimes we need to map those extracted oncological entities to their ICD-10 codes, or some procedures to CPT codes, or some medications to RSNOM codes. So we need to use the resolver models for this, and we have several kind of entity resolution models, which we will cover, and I will try to show an example in course while explaining these solutions. So this is what's happening at the behind for solving this problem. And first of all, we gather all the data and send it to the document filterer here. And after filtering the document, which contains the metastasis entity, and then we will tokenize them, those filtered documents, and get the embeddings of each tokens to vectorize, right? And after vectorization, we will also need the expert embeddings for the sentence entity resolver models, actually. So we use the expert embeddings, and then after getting the word embeddings, then we send it to the NER model to extract the entities like body part or oncological entities, and then we send those extracted entities to the assertion status detection model, just the oncological ones, because like body part entities doesn't make sense having the negation status, right? And then we will check the relationship between the body part and the oncological entities. And after that, we will send the results to the ICD-10 resolver model to map them, the detected entities, to their ICD-10 codes, and our result model provides also the billable information of the codes, so we can also get this information. So these are the models that we have just for oncology. Okay, we have 35 NER models and 7 relation extraction and 7 relation extraction DL models, and 8 different assertion status detection model, and 2 different classification sentence sequence classification models for biomarker and response to treatment. So why do we have these models? Like, why not we have only one model? Because of the requests coming from the customers and for solving the problem separately. Okay, sometimes we have some problems just for biomarker and biomarker results. So this model is for that, and this model is one of the generic one actually, which contains nearly 40 different entities, and this one is for anatomical entities. So this is why we have different kind of models. And also you can see that like some of them has some different extensions like healthcare or lung test. These models, like for this one, was trained with different embeddings. Okay, we train the models with different embeddings because sometimes they perform better on different customer data sets. So this is why we provide this kind of many models to our customers, and because we cannot know that which one will perform better on their side. Sometimes one of the model works well for one customer, and sometimes it doesn't work well for another one. This is why we have all these models. And for the entity extraction, we have 91 different entity detection labels. Okay, first of all, if you are looking for an entity, specific entity, like for example, like cancer operation, let's assume, and you just go to our model subpage and check the model which has that entity. And if you cannot find, even though we have 91 entity labels, if you cannot find your entity that you're interested in, you can also still have some, we have some entities which you can map that entity to yours. Like for example, cancer surgery. This is the same for the cancer operation, right? So you can just map them. We always help you to do that, by the way. You can just ask us and we can try to prepare a mapping for you by getting help from our annotators, clinical annotators. And even though we provide 91 different kind of entities, and if you cannot map your entity in none of our models, you can still use our zero-shot NER model, which doesn't need any fine-tuning, any like training, etc. You can just define your entity here like this, and then it is able to extract it. So you can just integrate it into your pipeline and use it with other NER models. We have 13 different assertion status labels. As you can see, like some of them are past, present, hypothetical, or medical history, or family history. This is one of the most important one actually. And like sometimes it is possible, and sometimes you need merged ones. So these are the assertion status labels we have. 5 different relation extraction labels we provide, like is date of is used for checking the relationship between the data entities and the other oncological entities or the procedures you're interested in. Like is finding of is another one, and is location of, like this checks the location of the oncological entities and the body parts. If they have a relationship, it labels like this. And this is the east side of, so like there are some tumor sizes and tumor findings. For some analysis, you need to check their relationships, and this is why we have these models. So for the entity resolution, let's assume that you have a clinical text like this one, okay, and you run your NER models in your pipeline on this text and like CTO, and you're interested in the procedures, and you would like to map the procedure entities to their CPT codes, CPT4 codes. So you extracted the CTO and an imaging text and abdomen as a body part, okay? And now this is a procedure. So we need to map this entity to its CPT4 code. But when you do this, just the CT, its CPT code is this one. And its resolution like this, like unlisted computed tomography procedure. But, for having better accuracy, you need to mention in the query about the body part, right? How you can do that, even though they were extracted two different entities, you can still do that by concatenating them. So this is why we have the relation extraction models. If you leverage the relation extraction models and if you check the relationship between them, they have a relationship. It's appeared, right? So, and when you query CT of abdomen, it is much more accurate than this one. If you don't want to use the relation extraction model for some reason, you can still use contextual resolution models we have, and you can just set some scopes from the left and right hand sides of the token detected chunk, like one from here, one from here. So this will be the query, which will return the same code with this one. Okay. So, and also, by the way, we also have different kind of solutions for the terminology mappings, like entity resolver models, which you can use, integrate just inject your pipeline and run with the NER and assertion and relation extraction model at the same time. Or we have vector DB resolver models, which are very fast and really good accuracy. And we also have a terminology server as another production we have. And you can just query your clinical terms, and it has a really big spectrum of the clinical terminologies. And you can get any kind of clinical terminology codes from there, from SUNAMED to CPT to MEDRA, for example, or like some all other clinical terminologies. It also provides an API, so you can do it via code. So we have a model subpage. I think you're already aware of that. And you can find the oncological demos on this page. And I will go over that actually and try to show you what kind of oncological demos we have. You can check the model performances over there. And these are the accuracy benchmarks we have with like some cloud providers. And for treatment, medication, anatomy, and condition, you can see that like we already have the best accuracy rather than the others. And this is the comparison of the oncological NER and the pathology entities versus ChatGPT, GSL versus ChatGPT. Sorry, not GPT-4 model. So you can see nearly all of them were past the GPT-4 model. And this is another benchmark that we got for IC10CM code mapping. And as you can see, it is apparently has a really high accuracy than the GPT model. By the way, you can check these blog posts to see the details of this process, and you can reproduce it because we have some notebooks on our repo, so you can use it. For example, this one, RxGenome code mapping with some other cloud providers and also the LLM model. And also Johnson Labs, like the Healthcare NLP library, 5 times cheaper than the other options, as you can see. I want to mention about the model training process, by the way. If any of the model doesn't work well on your use case and you would like to solve your problem by using the NLP tools, so you can train your model. This is how we train our model actually. Annotators annotate some data based on the prepared annotation guidelines, and then we try to get them aligned on the same policy for the annotations by setting a seed batch, and then we train the model until we get the best accuracy. And by the way, we upload the data set for annotators. For each batch, we train the model and pre-annotate the data and upload the pre-annotations to the GenAI Lab tool we have that we use for data annotation, and then export the data from there and train the model until we have the best accuracy. Or you can fine-tune our NER models with a small amount of data if you have. And this is another detailed explanation of the model training. So I will just skip it. And as the second use case, we will create a table for the biomarker and biomarker results. And let's assume that we have oncology nodes again, and we would like to create this table. And from the specific sections of the oncology nodes, because sometimes biomarker entities have the same writing with some usual words, right? And there may be some typos like from the doctors, by the way. So the models may get confused. So when you run all the document in the biomarker NER models, biomarker models, so they may get confused for the annotation in these cases. So we have another solution for this. Let's check how we do that. And we have the data. We will run that data on the sequence classification model to get only the sections that mentions about the biomarker. Okay. In this way, we will drop the sections that are not relevant that are irrelevant. Okay. And after that, we will extract the biomarker and biomarker result entities from those sections and check their relationships. And at the end of the day, we want to have this kind of biomarker result table. Okay, let's jump into code. Before that, let's go to our model subpage, and you can search any model from here, and filter some of them, like for example NER, and the language you can choose, and Healthcare NLP, of course. And this is the model. These are the models that you are looking for. You can, by the way, you can search by entities also. So this is one of the flagship models we have. It has nearly 80 different entity labels. It can label the clinical text with those entities. So this is a sample code that you can copy and paste into your pipeline in your notebook. And these are the results of this sample text. And another additional information about the model, its size, language, etc. And you can see the references for this model by using in-house data set it was trained with. And these are the benchmarks of this model. So you can also go to the demo page that I mentioned before. And in the clinical NLP, you can see many kind of specific topics like oncology, and you can find any model demos here like this in your oncology test, like in your biomarker. this model returns these entities. So you can see in a structured table like this, and you can do any kind of analysis on it. So let's go to the repo we have. Like we have Spark NLP workshop repo, and we will cover the notebook under the tutorials. Please go to the certification trainings, and under that, medical language models. We are already on here. Sorry. Yeah, here, sorry. And these are the training notebooks for this session, and this is the notebook we will cover, October 2025. So when you click on this, you can just click on the open collab and see the notebook like this, okay? So it is not possible to cover and wait for running all this notebook, but I will try. And you need to upload the license that we shared before with you. So then we download some libraries. And here we can check the models we have according to the needs, according to the topic that we need actually. Like for oncology, you can just type oncology or some other related entities, related tags here, so that you can filter all the models and see. And also, here's a table. These are the entity labels we have, and these are the NER models. So you can see some cross checks here if the model has that label. In this way, if you're interested in like the biomarker entities and you would like to extract the biomarker entities, you can just pick the models which has that entity, like this one, and add into your pipeline to have a much more robust NER pipeline and get the results, get better results actually. So it's still ongoing. And we will use 10 empty samples open source data set, oncological data set for our use case. And when we run this, we have such a data frame, and this is the sample output of one of the documents. As you can see, like there are some section headers here, there are some oncological entities and family history. These ones, these are the oncological notes, by the way, as I mentioned. So for the problem one, and we were interested in the metastasis entities, right? Because we are just trying to extract a pattern where the metastasis is spreading to. So first of all, you don't know which model fits for your use case, firstly, right? And these are the NER models for that are exist in the NER profiling for oncology pipeline. We have a one-line pipeline. Actually, we have a pre-trained pipeline which you can load it with a one line of code, and it's a quite big one, but it takes some time to load it. And when you have this, as you can see here, we have a sample text, and you can run your sample text on this pipeline as a light pipeline, actually, to get a faster result and check its results. Let's skip here and talk about this one, not to wait more. And this pipeline has all these NER models, and it can return all of the results of these NER models at a time. So you can see the sentence ID and begin indexes, end indexes, token indexes, and predictions of each NER model here, okay? So you can count the entities here in this pandas data frame. It is too easy actually. And then pick the models which are rich with the entities, or which can extract the entities best that you're interested in. After picking the NER models here, you can put them into your pipeline and create a robust pipeline and then run it on your data. But here we have just one NER model for filtering the entities, filtering the documents actually, which contains only metastudies. Here we have document assembler, and after getting the text data frame, here is the data frame we have, which is the patient ID and tags columns. And then we run it on your pipeline. We prepare the pipeline here. In this pipeline, we have document assembler. It converts the text type to a document type, and then send that to the sentence detector. Sentence detector helps splitting the data into sentences, and then we tokenize them. And after that, we vectorize all the tokens by using the embeddings model, then send them sentence, token, and embeddings information into the NER model, and convert them, because the NER model output is IOB tag. Okay, so we convert those predictions to chunk type by using the NER converter. Okay, and you can replace the labels, by the way, since we will need the body side entity of this model. So we just anatomical side entities later. We can just replace the body side with this one. You can manipulate your data by using these parameters, and then we send those documents. Actually, we already split them into sentences, so we sent those sentences to the document filter by NER, and this way we just filter the data frame. This is the data frame we run, and this is the document filter. This is the output, as you can see, because we set the metastatus. This filter filters the documents which has only metastasis entity. Okay, it doesn't allow, it drops the other documents, as you can see. So after filtering, actually before filtering, we can check the entity labels, unique entity labels here. As you can see, like metastasis, and metastasis here, there is just 3 documents which contains the metastasis entity. In this way, we filtered our all documents which has metastasis entity, right? Instead of processing all the documents and check and spend the resources, we filtered them and narrowed down our data set in a quite like. Then now we have to build the NER pipeline to extract the oncological entities, body part entities, and then we will process the data frame, right? So first we use NER oncology model, which has nearly, like here is the table, I will cover that, like it has nearly 40 different kind of entities, more than 40 actually. So, and we just interested in these entities. These are the oncological entities that this model can extract. Okay, as you can see, some of them are related to the body side, so we just map them to the anatomical side here, okay, by using the replace labels parameter. And after that, we use this model for anatomical entities, and we whitelisted here just the anatomical sites. And since we already interested in just this entity, right, we dropped all the rest of the entities. And NER GSL model, I already explained, and it of course contains some oncological entities and also the body part entities that we can use in our analysis. And then we use these models separately, right? All of them are extracted entities, but we need a single chunk at the end, right? So we use chunk merger annotator. This gets all the detected chunks coming from the NER models and returns a single chunk. So this is our final NER chunk. And after that, if you would like to filter some of entities, like you can filter some labels again, you can filter some specific terms like this one, you can do it by using the chunk filter annotator. You can create a black list or white list, for example. You can use that list in here, and all the predictions of this will be removed from your predictions. So we built a pipeline here and create the NER model. And this is how you can be sure that which labels these models have, right? This is the way. We have NER, we have loaded the NER oncology model here, or yeah, like this one. You can get this one and check its get classes method, sorry. Check its get classes method, and running this code, you can have the labels, all the unique labels of this model. So when we create a table with this, as you can see, these are the labels of just coming from this model. Okay, in this way you can filter or decide which labels you would like to use or which you would like to blacklist. So we have the filtered data frame, which has just 3 documents, as you can see, and it already has some columns. After running it in the filtering pipeline, it already has a text, document, sentence, token, and embeddings. And then we run this data frame in our NER model, which is the pipeline that we built. And as you can see, all the model outputs, all the component outputs actually in the pipeline shown as a column here. And this allows you to analyze the performance of the components in the pipeline, like specifically some of the models, if it is working well or not, or like just final chunk and filtered chunks, some more. So when we check for the results of the NER chunk, filtered chunk column, this is our column that we are using because it is coming from the chunk filter annotator. So when we explode the results, like you can see that its output type is chunk. This is the result actually. So begin and end indices of the chunk, result of the chunk, this is match, and the metadata, which you can find the sentence ID, chunk ID, and the NER source. It shows you where this entity is coming from, which model detected this entity, and its label as anatomical site, and confidence score, which you can set some thresholds for the models which are performing poorly, like this one, for example. If you would like to filter, like you can just set it as 0.8, and they will be dropped. So the embeddings here. You can use our Spark NLP display library, or I'm just using this one, and you can load it, and you can check the NER model performances by using this widget. And this is the final chunk. These are the entities that we are interested in, that we will use. So we strongly suggest you to save the results because you may need later, right? So, and for efficiency, if you will not need that, you can drop some irrelevant columns, for example, embeddings, if you don't want to need, if you don't need that later. But for the assertion model, we need this, as you can see. So we will keep it. And some of the columns can be dropped for efficiency and keeping the resources in optimized way. So in the second step, we use assertion status detection model. And as I explained in the slides, body part entities doesn't make sense sending them to the assertion model and having their like negation statuses, because it doesn't make sense. So we will just get the negation status of the assertion status of the oncological entities. Okay, so there are several ways to solve this problem. You can create another chunk merger, which you will use just feeding to the assertion model and filter the oncological entities that were extracted, or you can use chunk filter again and filter the blacklist the anatomical site entities, and rest of the entities will be fed to the assertion model, as you can see. And then, because sometimes, and then we filter just the present ones, because sometimes in the clinical notes, doctors mentioned about the entities which are absent, like no cancer detected, for example, or her father has colon cancer history. Like this kind of informations doesn't allow us to drop them without using the assertion model, because NER models detect those entities like colon cancer as an entity, but we cannot know that if it is the one that we are interested in, right? It is not related to the patient herself or himself. So we just filter the present ones in this analysis, okay? Sometimes you may need to filter just the past ones for the patient's history, okay? And we run our data frame, NER result data frame on the assertion pipeline. As you can see, this is the column that we are interested in. And then here is the result visualization of the assertion output, okay? As you can see, we just have the present entities here. So this is the output of the assertion filter result. This is the chunk, then sentence, chunk IDs, assertion label, and NER source shows again, and NER label, and the confidence score of the assertion model. Then we have a table. We created a table like this: begin and indices, patient IDs, and the NER labels and assertion labels. Then we say the results, and after that, we already extracted the oncological entities and body part entities. We check the assertion status of the oncological entities. As a third step, we need to check the relationship between the body part entities and the oncological entities, right? So we use the relation extraction model here. As you can see, we create the relation pairs and run this pipeline and check the entities if they have a relationship. As you can see, like chest wall lesion, okay? And after that, after running the relation extraction model, we have such a table like chunk 1, chunk 2 here. These are the indexes of the chunk 1 and chunk 2, and these are the entity labels. And these are the relationships which they have. So that we need to filter this table because there is no associated information here. We can still have some entities, chunk 1 or chunk 2 entities, which are not present, okay? So we need to drop them. And for filtering them, we need to merge the assertion data frame. Sorry. So we need to drop, we need to merge the assertion data frame with the relation extraction data frame, right? To check the assertion status of the entities that are in the relationship or not. And this is the final data frame we have. And after filtering that, we need to concatenate them if they are present, right? So like this one, for example, lesion and also neck, and they have a relationship and they are present, like the lesion is present. So we concatenate them, lesion, neck, and this is the neck lesion actually. So this is the data frame we have at the end of all processes. So why do we need this? we need this because and these are the present ones. So we created new chunks, right? And after that, we need to concatenate our relation extraction results with our oncological data sets, oncological results, entity results, because we will get the ICD-10 codes of these entities. So here we explained, actually, let me show you. Why do we use the relation extraction models? Because when we query the cancer entities on the ICD-10 resolver models, we get this result in any kind of ICD-10 lookup table. It returns C80 for the cancer entity. But if it is lung cancer, the code has been changed. Okay, and sometimes this is this code is maybe believable, but this one may not. So this is why we need this process. We make it more granular and much more accurate. And after that, we have a data frame, which you can see some duplicates, like this one, chest wall lesion happened 2 times, or like breast adenocarcinoma happens 2 times. So we can drop the duplicates. Because why? Why? Because we will use birth sentence embeddings here, which is expensive for the resources. Okay, so we just get the embeddings of the unique ones and run them on the resolver model. We run the chunks, by the way, and not the sentences, not the text. We run the chunks. This is also possible to like copying here and adding to your pipeline, but at this time you need to run all the entities here. So this is why we filtered and dropped the duplicates to optimize the resource usage, and of course, it speeds up the process. And here is the output of the resolver pipeline. And when we merge this, we have created a table with the chunks and the patient IDs, chunks, their ICD-10 codes, the resolutions of the ICD-10 codes, and all other possible codes sorted by the distances and their resolutions and the billable informations here. So for example, like this lesion ICD-10 code is missing. So when you query this lesion ICD-10 code, the result is this one, and its resolution is this one. Okay, this one is much more accurate, as you can see, like net lesion. So this is the code, this is the resolution. But if we just use the lesion, this is the result. And then we save the results. For the second problem, how we can create the biomarker and biomarker result table by only getting the information from the specific parts of our documents. So we created an all-in-one pipeline. You can see everything here. We have document assembler, sentence detector, tokenizer, and workforce sequence classification model. Why? Because we want to filter the sentences which contains the biomarker information. Okay, and then we filter those sentences and send only those sentences to the word embeddings, linear models, and converters. And also, of course, for the relation extraction model, we use the perceptron model and also like dependency parser model here, and build a pipeline. When we run this text, it's a sample text, by the way. So we fit our pipeline and transformed our data, and this is the result, by the way. And when we explode the results, this is the sentence IDs. These are the sentence IDs and their results, like classes. Classes means if they are related to the biomarker or not. Okay, as you can see, there is a biomarker here. So it says it is one. Okay. And then we filtered those documents. By the way, these are all happened in this pipeline. I'm just exploding the data frame, exploding the columns that we have in our result data frame. After filtering the sentences which contains biomarker, and then we sent them to the relation extraction model, right? Entity extraction model, sorry. And after extracting the entities like biomarker and biomarker result entities, we got the relationships between them. And as you can see, some of them are in a relationship, but some of them are not. So we need to drop those ones. And this is the final table that we have at the end, like this one. So this is the biomarker and biomarker result table. So you can also do that like LLM and Q&A summarization models, and this is sample text, and you can load this model and like ask question here, summarize the patient's relevant medical history, including past procedures and conditions. It summarizes, and like this one, this is summarization, and this one is summarization, for example, and then run those summarizations to the in the NLP pipeline. Or you can use the zero-shot oncology NER model, as I mentioned. If you don't have, if you cannot find any relevant NER model that cannot extract the entities that you're interested in, so you can use this model by defining your label here. That's all. It can extract the entities like this. So thank you so much for listening. I think after 10 minutes, and my other friend will present the yourself actually present the other session, and then it will end. So thank you so much for listening. I will be at the behind for answering questions.
Okay, this is the final session of this day, Wednesday. So I'm going to discuss the rare disease diagnosis and our solution for accelerating, because we know that it takes a lot of time and a lot of doctor visits until you get a diagnosis if you have, or if anyone have this type of disease. And as I said, we have a solution for that. I prepared the notebook. Maybe I should first show where is everything. So this is not the notebook I'm going to discuss. It's already uploaded. So if you go to our GitHub repo, the links were shared already, but the notebook is right here. You see that HPO rare diseases, and the slides are right here again, rare diseases. So let's see. So I'm going to start by defining phenotypes, what they mean, their importance in detection, and Johnson Lab's solution for that. And then there is a ClinFan library developed by Stanford researchers a lot of time ago. There are some other libraries, but ClinFan is like the reference in this area. And then we use various LLMs to also extract the phenotypes and their the HPO codes. And we're going to make a comparison. So let's see. What phenotype means is it's like in some cases it may be signs and symptoms and like clinical findings, lab results, but not always symptoms. I mean, they may have different meanings. In some cases, in some diseases, you may just say symptom, but if it is related to a rare disease, then we have a problem, and we try to understand them early. And some lab results and some MRI findings. So this visual is very important. I'm going to spend some time on it. So the definition of rare disease is right here. It's if the disease affects less than 200,000 people, it's defined as a rare disease. And rare, but it's not too rare. You see that 30 million people in the USA are affected by disease. So it's a little less than 1 in 10 Americans. The statistics is similar for globally. And the bad news, another bad news, is like 7,000 different rare disease and disorders. And still bad news, you see that 95% of the rare diseases, there are no drug treatment. There is no FDA approved treatment for 95%. So which makes only 5% may be treated. And the other thing is, I don't know if we can do anything, but the 80% of the rare diseases are genetic. So you can't do anything to your genes, I guess. And so the other one is, I mean, I'm gonna again spend some time, but the one on the left, lower left corner, very difficult to get a diagnosis for this. You see that you have to maybe average 8 visits to a doctor, and it's gonna be, you're gonna start with the family doctor, PCP, then you're gonna go to or visit different specialists until you are gonna get a diagnosis. And diagnosis will not solve everything. And our solution, I mean, Johnson Lab's solution, we try to decrease this time and physician visits. And the other one is, you see the misdiagnosis, the average number is 3. It's too bad. So it takes around 7 years until you get a diagnosis. And as I said, around, you see that 6% of the world is affected by these diseases. The difference maybe between the USA and the global is in some areas of the world, there is no diagnosis. So you can't just increase, I mean, you cannot trust this number. So as I said, you have to visit doctor many times, many different tests until you get a diagnosis. So take a look at the horizontal axis. So let's say the symptoms start at 0 years, and then you go to the doctor in a year, in less than a year, and then you have to visit multiple doctors in the first 3 years, and then you get an accurate diagnosis in around 6 years, and in some cases more. And so HPO, the definition of HPO is like the, it was discussed in yesterday. I started with the ICD-10 codes, RX norm codes. So there is also a specific coding system for the HPO, for the phenotypic abnormalities. So they are called HPO. And there are around 18,000 terms right now, and increasing probably. And so each HPO term defines a specific phenotype problem, not the disease or syndromes. I'm going to show you a table or data frame, and you're going to see the difference between them. So there are hierarchy. So we are interested in the parent system. I mean, we get a phenotype, get the HPO number. We are also interested in the synonyms and the parents. So yeah, this one is quite important. So the middle column, the phenotype, the name of the column is phenotype. The doctor can get these. I mean, these are mostly like symptoms or which can be understood by the doctor. But the phenotype does not mean it's a disease. There is a HPO code for this phenotype, and they point to a certain disease. I mean, this is the diagnosis phase. So you get the phenotype, or the doctor observes the phenotypes, some of them by some tests, and then you get the diseases. And in our solution, we try to remember, this is NLP library, so NLP and LLM, let's say, we are working on extracting the important information from text, unstructured data, let's say. And what we do here is we start by the text, try to get or extract all the phenotypes, get the HPO codes, and do this accurately. And then we try to help the doctor make the diagnosis. We do not make the diagnosis. The doctor makes it. We support the doctor. And yeah, there is a problem. It takes time. I mean, we work, I mean, I work as a data scientist, but in our team, we have many doctors, and I discussed with doctors. We do not always agree with these. I say that, okay, let's say many PubMed articles you checked, and it says that human experts or annotators take or spend more time in understanding the phenotypes. She says no. She says the doctor is better, or maybe RN is better at this. And I say that, I mean, again, not my opinion, but PubMed article says that there are inconsistencies between different doctors' opinions, and she says no. So these are not carved in stone, but there are differences. And this one is good. I mean, this visual is good. Blue is manual process, which means that performed by a doctor or a RN, let's say. And the green shows, let's say, our solution or automated solution. Let's say you call it ClinFan, LLM, JSL solution. But the first one, time to diagnosis, you see that this is expected, actually. I mean, manually it takes more time. The automated solution takes only 40% of the time. This is expected, no problem here. And the other one is similar to this one, expert time required, yes. And again, the library, our library takes less. I'm talking about the middle two axes here, two, let's say, numbers here. So phenotype coverage says that our solution maybe covers 90% of the phenotypes. The doctor or the expert has only 60%. I can't argue with this one. Consistency is the problem. As I mentioned, I discussed this with our MD and one of the MDs, and she said, no way, we are always consistent, and the PubMed says no. So I'm gonna just leave it here. So we use this reference data set. You can follow this and take a look at this, but it is similar to this one. So we use this one in preparing the solution, like starting this one. This is the phenotype, abnormality of body weight. This is the HPO code, and there is a synonym here. It's not a synonym, excuse me, it's a synonym, but it's an exact synonym. Let's take a look at this one, this kidney problem. Again, the kidney problem is mentioned here. HPO code is right here. And then you see that there are 3 exact synonyms. These are here. And so it goes like this one. There is the UMLS code. Remember, you also have the UMLS code in our solution. And let's get back to the, yeah, we use this data set. You can take a look at the GitHub. Again, follow the link for this one. Yeah, the starting point was around 1 year ago. I was part of this team. We started to train an NER model. Normally, our solutions used to, let's say, not always, but almost always, we start by training an NER model, get a reliable data set, and then train a model. But the problem was, as I said, phenotypes, some of them are symptoms, some of them are like signs. So the NER model was not so good at extracting it. In most of the NER models, the model will have problem with extracting between or differentiating between a symptom, sign, symptom, and the disease. So this is always the case, and it didn't work. So we worked on this alternative solution, and it includes some fuzzy matching, lemmatizer, and it's a huge pipeline. I mean, multiple stages. So the pipeline at the end, I'm going to go to the notebook to work on it, but it's going to be, the stages will be, we get the phenotype, then get the HPO codes from them, and if needed, we will map them to other, like the synonyms, parents, UMLS codes, and similar, and genes and gene-related diseases in the other stages. So yeah, that's what I was trying to say. This visual shows what we say. I'm going to get this one first. So take a look at this one. So this is a sample sentence. You see that these are fever, seizure, hypotonia. Looks like some of them are symptom to me. So the pipeline is going to take a look at this sentence and then extract 3 entities here: fever, seizures, and hypotonia, label them as phenotype, and then get the HPO codes. Again, the pipeline is going to provide you the HPO code, and then it's going to provide the synonyms here, and the synonyms will be 3 different stages, like the exact synonym and then the other ones. So we are going to discuss this one. And if they are, I mean, we don't always say the UMLS codes, but if they are in the system, the pipeline also is going to give you the UMLS codes. And in some cases, these are the phenotypes are related to genes, as you can see on the rightmost column. And we don't see it here, but we are going to discuss this. The gene, you get the related gene related to the phenotype, and then you may also have the disease. So you see that this is quite a supporting system for the medical doctor. So one thing I didn't mention yet, so take a look at this one. So the first stages, as I mentioned, they start with the text. The pipeline is going to give you the human phenotypes from the text. But there is the assertion or negation, and this is quite important, because maybe in the text, the doctor takes notes and says that the patient had fever 2 years ago. Right now, he's okay. And let's say he says the patient had seizures, but he stopped having seizures, type of thing. So the assertion model is going to say, okay, so this is not a phenotype, or at least it's a phenotype, but we are not interested in this one. Or maybe the text will say the patient's mother has hypotonia. If you are only interested in entity extraction, you're going to get everything. But some of them should be eliminated by using the assertion model, with a reliable assertion model, let's say. And this is a huge stage for us. And then we get the HPO codes, and then these are optional. So you get the UMLS codes if you are interested, then get the genes and diseases, as I mentioned here in this data frame. And then get the parent terms, I forgot to put them here, and then mappers to get the synonyms for phenotype. So I will switch to the notebook here. So this is the notebook that you're gonna see in the repo. So start with these things. I already started the notebook, but I'm not gonna run it. So I got this sample text here. And so in any case, when you work with the Johnson Hall Labs library, you first run in this case, it's a pipeline. Sometimes you define the pipeline, and in these stages, you will define the models that you're going to run. And in this case, I run the HPO mapper pipeline. We discussed this. I mean, many presenters said that, but the nlp.johnsonhall.labs.com, it's a very important page. It's a reference page. So I just click on models here and then paste HPO mapper pipeline version 4, and this one is version 4. So you go to the pipelines homepage. So what you see here is you see that there will be multiple stages. You may be interested in these stages, and you can make modifications in these stages if you want, if you know what you are doing, or you know the details of the stages. So this is the size of the pre-trained pipeline. You only download it once. So this one is 610. Right now we are working with 611. So any license newer than 610 will you will be able to work this one. And then let's say, yeah, this is a short description of the pipeline, how you work it, what it does. And if you're working Python, it's, as you say, you just import the annotator here, but it's a one-line code. I mean, you don't code anything. You just call the pre-trained pipeline, and then you full annotate here, as we are going to do in the notebook. So this is a sample text, and you're going to get all of these. Remember, Spark NLP, we work on Spark. You work with the data frame. So for every stage, you will get different columns. So the starting point is, do we have any? So you see that we have a sentence detector. So the pipeline starts with splitting the sentences first. And once we get the sentences, we get tokens for each sentence. So this is the begin and end indices for the chunk. So this one is the first chunk, or the phenotype for us, apnea of prematurity, and assertion says yes, it's present, it's not absent. So this column says that, okay, the HPO code for this one is right here, and then HPO code and definition is right here, and it's a parent, by the way. So UMLS code, we don't have the UMLS code for this one, but we have the code for the second one. And EOM mapping, we're going to discuss this one. So this one is gene and disease. So not the first one, but the second phenotype is related to this gene, and these are also maybe related to other diseases. So it's a huge help for the doctor, I guess, to make a diagnosis. And then we go to the synonyms column. You see that some of them, I mean, almost all, but not all, have exact synonyms. Some of them, not here, in our example, maybe related synonyms and broad synonyms. So it's gonna provide you the exact synonym, which is important. The other one is provide you the related synonyms, which will also help in decision making. And also it's there's a broad synonym. So let's get back to the notebook again. As I said, you download it once. So once you download it, the first time it's going to take some time, but the next time it will be much easier. So I just full annotated this one. I was only interested in HPO term, but the HPO term also brings some metadata, like the respiratory disease was in the, yeah, respiratory distress. distress was in the first sentence. Yes, it's right here. Begin and end indices, the HPO code. The HPO code is defined right here, I guess. Yeah, right here, HPO code. So you can just, I got the key so that you may be able to run these. I mean, change HPO term with HPO code and see what happens. Or you can just remove this one and run it. You're gonna get some, let's say, a lot of information here. And you can take a look at this one. So this is light pipeline. We discussed this yesterday. Light pipeline, normally we use for less data. It's not mostly used for production. It's used mostly to see how your model or pipeline is working. It's just it's gonna give you some idea so that you will handle, I mean, most of the time, the users of the library use batch processing, like 100,000 documents. Some users are interested in just getting like 5 documents. Let's process 5 documents, and then you see there is a lot of information here, and you can pull all of these and take a look at these. And as I said, some of the users just take 5 documents, 5 clinical texts, and then get the results. So light pipeline is quite easy to use. So maybe it's too much here. So normally what I did was the fit transform. Remember, it's like getting the prediction. Full annotate is also get the prediction. So we have the model, we just define it and then get the full annotate, and then we have the results here. So you give the text, you get the results. And in this case, just a little lines of code. I'm interested in the chunks here extracted by the model, begin and end indices, and then the label here. There is only one label here, HPO, so no problem with that. You just run it. You see that there are only 12 phenotypes in this model. And again, we discussed this one yesterday. This is NER visualizer. It's quite helpful to see the model's performance in the early stages. Again, you don't use it in production level notebooks. You try to see how your pipeline or model is working, if it is missing something or not. So in this case, I just run the NER visualizer to see. I just feed HPO term here. Result is right here. You can save it as an HTML file. And this one is quite important. This one is, in this case, remember, we have the assertion model in the pipeline. So we get the extracted entity here, again the HPO here, label is right here, same data frame as the previous one. The only thing is we added the assertion column here. So you see that these are almost all present. Only thing is this one is absent, and anxiety is related to someone else. Let's see if it is really this case. So the NER model works on top of the assertion models works on top of the NER here. So you get the NER, you extract the entity, label as an HPO, or it's a phenotype, which means it's a phenotype. And you see that it's labeled by the assertion model as an absent. So the reason is the assertion model uses context here. In the context or the text, it says there is no evidence of conjunctivitis. I don't know how to say that, but it's related to some eye disease. So you see that there is no evidence. That's why it labels, the assertion model labels as an absent. And in the second case, this is associated with someone else. Sometimes we use different labels like the family. And in this case, you see that there is anxiety. I mean, it does not say it's absent, but it's maternal. So the anxiety is the patient's mother actually has the anxiety. So that's why this assertion model is very important. It has to be in these stages, but and also it has to work accurately. The other one is, and then in the next stage, we have the extracted phenotype here, the label, assertion label here, and then the HPO code. So we get the HPO code here again. I didn't add a visualizer, but there is also an entity visualizer. So again, if you go to nlp.johnsonolabs.com, you go to documents, Spark NLP. It is supposed to be somewhere around here. Yeah, Spark NLP display. So you see that we have a visualizer for NER. We have a visualizer for entity resolution, which is HPO code in this case. We have a visualizer for RE and assertion. So let's take a look at this one. This one is for dependencies. So this one is a NER visualizer, quite useful, as I said. And this one is relation extraction. Again, in this case, problem and test, relation between problem and test are established here. And assertion visualizer is right here. We discussed it. And this one is the HPO code. So I didn't put it here, but you get the HPO label here, and then the HPO code, and then the definition of the HPO code. So it's right here. The other one is, as I said, we use light pipeline. It's also possible to use transform here. You see that we have the medical pipeline. We've already fit the model, so we just transform it to get the results. And once we get the results, we use flattener. Flattener is, let's say, I guess it was introduced to our library in less than a year. It's quite useful. The Spark data frames are not so good looking as Pandas data frames, so flattener makes them look much better. So again, no problem here. It just shows you the results. And I just get the HPO code here for, again, using the flattener here. You define what you want to see here. We get everything from metadata, as you see. So the respiratory distress was extracted by the entity resolution resolver, let's say. And then we have the begin and end indices, and then the HPO code. Assertion, remember I said that it's quite important. So again, we get the respiratory distress, the phenotype, indices, and the assertion status here. And you also have a confidence level. I am not so sure about the confidence level. I mean, 100%, I don't think so, but it can give you an idea. You may also filter the results by using the confidence level. I mean, if it's 20%, yes, probably it's not so accurate. And so let me get back to the okay, so we remember we have 5 mappers here. You can use them separately. You can call these mappers like this here. The HPO synonym mapper, it's in the, again, I hate switching back and forth, but let's see, it's nlp.johnsonolabs.com, and the name is HPO synonym. So I'm in the models hub. So you see that we have different mappers here. So in this case, you're gonna work with synonym mapper. So just click it, and you see that it's introduced in September, only 1.5 months old, and it's a small model. Mappers have no problem. So like this one, fatigue, neoplasm, anemia, you see that we get all the exact synonyms here. I don't know if, yeah, for at least the first one is shortness of breath. So abnormal tissue mass. So it's quite useful. So I'm going to go to the so the synonym mapper, you can run this separately, and you just juggle and get this data frame once you annotate or transform it. So the term is shortness of breath, but in this case you have to give the phenotype to this mapper, and you're gonna get the exact synonyms like this, and related synonym is here, and broad synonym, yeah, this one is good. So it's shortness of breath, but the broad synonym says that it's respiratory distress. So the other one is, yeah, just this visual. So the blue ones, the blue notes, let's have some kgs here. Blue notes show you the exact synonyms, and this one is in the scope like the sum. This is the phenotype that we're interested in. Once we get it, we can use the synonym mapper by separately, or it's already in the pre-trained pipeline. And then we have related synonym panting in green note, and then the broad synonym respiratory distress is right here. And parent mapper, remember, we can also, once we have the phenotype, we can go to the parents here. So this one is interesting. So let's say we get intellectual disability or seizures. This one is more detailed. And you see that seizures, okay, we have the HPO code, and immediate parent, one level above, let's say, it's abnormal nervous system physiology. And it's if you can get for some of these phenotypes, actually, the highest or a higher level ancestor here is abnormality of the nervous system. So seizures are related to the nervous system, and you can get the immediate HPO code, and then comes the HPO codes for the immediate parent, and then in the last column on the right, you will get the HPO code again, this one for abnormality of the nervous system. And then this one is quite important. As I said, you can run this as a separate solution, or we already have it in the pipeline. So once you have the phenotype and the HPO code, the pipeline is going to give you, or you have the option to get the related gene like this one, and then the result clinical feature or the disease here. So like this one, I forgot to put the phenotype here, but the HPO code is right here, related gene is right here. So there are 7 related features in the result clinical features. So it's quite useful. And again, this one is UMLS mapper, and this one UMLS mapper is in the again, I will just switch to this one, and let's say HPO UMLS mapper here. Yes, this one is newer. So remember, for standardization in healthcare, we use different ontology. Like I think the most widely used one is ICD-10, and for disease and symptoms. SNOMED is also very important. Many different codes, and they update regularly. ICD-10, I guess, update the codes every 6 months. And we have RX norm for the drugs, and then CPT for the I guess for the different tests. So in this case, UMLS, getting the codes for UMLS codes, I mean, getting the codes from the HPO codes is quite important. As I said, you go to the page, you don't have to run the whole pipeline, but you can run this one. The only thing is you have to provide the HPO codes here, like this one, if you use the HPO mapper separately. But if you use the pre-trained pipeline, then no problem. The the you remember the stages for the first one. This is the mapper pipeline. That's the whole pipeline. So in one of these is, remember, we have synonym and then mapper, and then the parent mapper, and then the UMLS mapper, and then the well, I remember there is EOM mapper, and then gene disease mapper. So all these mappers are right here. You can use the whole pipeline, or you can provide, in this pipeline, the HPO codes will be generated, or you can just provide the HPO codes, and this mapper is going to give you the UMLS codes like this one. So it's quite useful. Oh, sorry. So let's go on with this one. And I'm going to say a few words about the ClinFan library. It's also in the notebook. So let's say we have the synonyms here. We discussed this one. Parents, quite important. UMLS, gene and diseases. This one is, I mean, it's all, remember, around 80% of the rare diseases are genetic. So getting the genes and gene-related disease, the providing this information to the medical doctor is will be very helpful. So EOM is related to these extraocular movements. So you can also get these codes. I mean, start with the HPO codes, and you are going to get the EOM information also by the pipeline. So I added a separate section for ClinFan library. It's quite easy to use. You just install it, and then just a few lines of code here. So I put the note here, and also then I'm gonna use our text here. So in the first one, fused nails and teeth. So you remember this one. So both the nails and the teeth are fused. When you run it, and I'm going to show you the results of both the LLMs, Johnson Labs, and the ClinFan library results here. And you know that, or you see that these are the fused nails and teeth is related to this syndrome. So this is the output of the ClinFan library. It provides you the HPO code. Good news, fused nails. The problem here is, you see that it's rule based, so just misses the second section. Just keep this in mind, and we are going to discuss the comparison in the PowerPoint slide. So in the other one, remember anxiety. Remember, in our case, it's maternal anxiety. So the assertion model is quite basic in ClinFan library, so it missed the anxiety here. So although the anxiety, the mother of the patient has anxiety, it just assumes that the patient has anxiety. Although, let's go to the sample. Yep, assertion here. Conjunctivitis, the ClinFan library assertion system worked and did not extract conjunctivitis. So I'm just gonna switch for the final time, I hope, to the slide. So let's see, it's a tool designed to get the HPO terms. Okay, no problem. Starting point is a free text patient records. It's like a similar to an NLP, just focused on HPO codes. It's just trying to get the phenotype mentions in the text and try to map them to the HPO. It's a basic, let's say, dictionary. And you see that, I mean, it's only one example. Maybe we cannot generalize, but there is an assertion system or negation system, but it doesn't always work well, or does not work perfect. So no seizures observed. Probably it will work, because no, it's rule based. So if you see no before the phenotype, just negate it. Probably it's in one of the rules, so it will work probably. And so the basic HPO terms it's going to extract, but some of them it will not be able to get. The other thing is there are around 14,000 items, and right now there are more than 18,000 HPO terms. So these are missing, and they have a different approach here. I got this from their paper written in 2018. So they don't use tokenizer. You see the stages here. So start with this one. The clinical note is right here. There is not a perfect sentence system, but I guess they use some character, number of characters limits the sentences. So you see that right here, it's per sentence. The second one is just divided in the middle. And then there is, as I said, there is no tokenizer, but there is some sentence parsing here. So these are right here. So short stature is extracted okay. HPO code is right here. Long eyelashes are right here, clefts. And this one is immediately, the definition of small jaw is right here. So this is how the ClinFan library work. And so the problem, you see the problem here? Her father has short fingers and long toes. So there was a problem in extracting these. And so we also used a couple of LLMs here. One of them is Gemini 2.5 Pro. Yeah, we know that we use LLMs for everything. It's like the Google a couple of years ago. We tried to get every information from LLMs here. So that's why we worked on these. We wrote different prompts, very strong prompts. We know that the LLM will be very successful in getting the phenotypes. The only concern was about the HPO codes. So, and the other thing is, if you want to do scaling, if you want to work on millions of documents, it's going to be very expensive. So also hallucinate, it's always a problem. So negation, I don't know. I'm not so sure about negation. Normally, the LLMs were quite good with negation. So the only concern, or my concern, was, okay, phenotype, it's going to find, I know that LLMs will be successful in extracting the phenotypes. Assertion will work. Not so sure about the scaling, by the way, but the LLMs may have a problem in getting the HPO code. So it's going to provide you some code, but it's probably not so accurate. So we use the data sets for testing. Tested the data set for everything. Our solution, ClinFan, and the LLMs here. There is only, we use this training data for NER and did not use it for training anything else. So there is no data leak here. And as you see, there is present, absent, or associated with someone else in the entities. Once we solve them, we just remove them. And we have the HPO codes here from the reference data. So the thing is, if the LLM or ClinFan library, if they contain the target chunk, we said, okay, that's correct. And for ClinFan, the output is provided as phenotype. There was some problem with that. And in some cases, the exact target chunk is returned. In some cases, a synonym appeared, and that's a problem. And you can't do anything on it. So coming back, the assertion, we said, if they are labeled as absent or associated with someone else, we didn't consider these as valid HPO terms. And if ClinFan also works similarly, I discussed a lot about assertions, so we expected better results. So what you see here is, this is what we did. I didn't expect this much. 97, 98% plus. It's a little too high. Gemini Pro 2.5. I know that Gemini or OpenAI model, we expected the chunk accuracy to be high. It's okay. And synonym, we didn't expect too much. I mean, we tried to focus on this case, but ClinFan for 4.990, it is too low. And the HPO code, we know that the LLMs will not be too good with extracting the HPO codes, but this one is, so let's say this one is bluish for LLMs, and very good news for us. And the HPO code, this is definitely not blue for LLMs or ClinFan. So let's say I got two examples here. One of them is good news for us, the bottom row. The other one is also we had a problem here. So this one is we try to focus on hypoproteinemia, which is just low protein. So we give it, send the prompt, and the OpenAI just shows us hypoproteinemia. You see that all four solutions give us the correct solutions. Gemini 2.5, I don't know why this came here. I mean, the synonym is low blood protein, which is okay. Yeah, this is correct. But the second HPO code is not correct. And the other one is, once you get the lymphatic disorders, the synonyms are also not so good. We got the top score here. The second one is, this second example is, yeah, remember this one, fused nails and teeth. The problem is, fused is like an adjective defining nails, and also fused defines teeth. But the problem is, I mean, not the problem, start with the good news first. The OpenAI was able to extract both of these, but the HPO codes were incorrect, and synonym, there is no synonym. Gemini is okay. You see that it's also correct, but the HPO codes are not correct, and synonym is right here. Yeah, this is nothing to do. I mean, yeah, similar. So ClinFan and JSL pipeline, fused nails, they were okay with extracting the first phenotype. Again, let me say there are two phenotypes here. One of them is fused nail, the other one is fused teeth. And they all provided, I mean, both of them, ClinFan and JSL, provided the first phenotype correctly with the correct HPO code, but nothing about the second phenotype, which is fused teeth. So we are going to make corrections for this one, and we get this synonym from the JSL pipeline. So do we have anything here? No. So finally, let's make a small conclusion. Yes, they are very critical for diagnosis of rare diseases. I mean, the information is right there. I mean, if the patient visits, like you remember a cancer patient, many visits, all the details, symptoms, test results, and all the treatments. In similar case, in rare diseases, the phenotypes are there, but it's very difficult to make a diagnosis out of unrelated phenotypes. So the Johnson Webb solution will be very helpful in getting the diagnosis. So we cover over 18,000, and automation supposed to be very helpful, and unstructured text into structured. Yeah, TLDR, I like this one. We try to accelerate rare disease diagnosis through AI-powered phenotype extraction. Thanks for listening. Let me see if there are any questions here. Okay, nothing for me, I guess. Thank you. So NS, you have the decision to make. Thank you.
Thank you, Gustav, for the session. So I'm closing the session. You will receive the links for the recordings after the sessions. So see you tomorrow. Bye-bye.